Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, I'm Madan Muswati from the Research and Software Engineering Group, and it's my utmost pleasure to introduce Jun Feng today. He is an assistant professor at Columbia University, and we go a long way back. We met in graduate school, so he worked on model checking as well, and he applied model checking to find lots of errors in the Linux file system, and then he moved on to apply those techniques to distributed systems. And recently he's been working on reliable multi-threading, how do you get deterministic semantics to multi-threaded programs. He recently received an NSF Career Award for this work, and so it'll be exciting to hear more about it. Jun Feng?
Hey, thanks for the introduction, and thank you guys for being here. Since this is a small group, if you guys have any questions, feel free to interrupt me, right? I actually tend to explain things better if it's more interactive. So this talk is about our recent work on making multi-threaded programs more reliable. And the key idea here is called schedule memoization, which I'll explain in detail in this talk. And this talk is based on the work coming from two papers, one OSDI paper, and the system is called Turn, and another paper, SSC paper, the system is called Peregrine. And this is joint work with my students, He Mingcui, Junyue Wu, John Gallagher, Haiyang Guo, and Jiazhe Cai. So these are great students. I enjoy working with them. If you guys are looking for internships, looking for interns, right? We actually want to talk to these students. Okay. So let's look at a few trends that shape our computing today. The first trend is a hardware trend. The machines are getting more and more cores. So this slide actually shows the number of cores for AMD Opteron processors. As you can see, in 2010, we have 12 cores on the Magni cores processor. So how do we use all these cores? Developers are writing more and more multi-threaded code. The second trend is a trend in software, the coming storm of cloud computing. So we have more and more users connect to the cloud of servers. We have more and more devices connect to the servers as well. And this creates lots of computation. At the same time, the computation actually is aggregated on these servers in the data center, right? So how do we get good performance in this setting? Well, for performance, virtually all these servers employ multi-threaded programs. So at the same time, multi-threaded programs are not difficult to get right? They often contain the tricky hidden bugs, right? Data races, for example, that sometimes show up, sometimes disappears. It's really hard to write tests and debug these multi-threaded programs. And the key reason I believe, and also my other researchers also believe, that these programs are non-deterministic, right? When you run them, it's like you're doing a coin toss. Sometimes you get heads, sometimes you get tails, right? Success or failures. So specifically, today when we run the multi-threaded programs, even when we run this program on the same input, right? We run it repeatedly. Each time we may actually use a different thread interleaving or schedule, right? This rectangle represents an input. And each time we run it, we may get a different schedule. So essentially, there is a one-to-many mapping from inputs to schedules. So this non-determinism actually complicates a lot of things. For example, testing becomes a lot of less assuring, right? Many of these schedules are actually good, do not contain bugs, but some of the schedules contain tricky errors such as data races or these concurrency errors. And when we test a program, we may run into these good schedules, right? Therefore, the bugs did not show up in the testing lab. But once we ship the code to end users, when they run the program, they may trigger these rare interleavings where the bugs show up, right? Get crashes. And similarly, debugging becomes very complicated because in order to track down this bug, right, we may have to reproduce the same bug interleaving, which can be challenging. So recently, researchers have proposed a great idea called deterministic multithreading, which conceptually forces the program to always use the same schedule on the same input. So essentially, there is a one-to-one mapping for existing DMT systems. When we run the program on the same input, regardless of how many times we run it, each time we always run into the same schedule, right? So this idea is great. It solves a lot of issues caused by non-determinism, but at the same time, these existing systems they actually suffer a limitation if you basically make the schedule tightly dependent on input. If you change the input slightly, let's say you just change the input by 1 bit, for example, and these systems may force the program to run into a very different schedule, which may also contain bugs, right? So there's this tight sensitivity, input sensitivity, the tight schedule input dependency for existing DMT systems. And as I just mentioned, right? So some of these schedules also contain bugs. And this will complicate testing as well because we can test some inputs in the testing lab, right? But we cannot cover all the inputs. But when we ship the program to end users and they run on some slightly different inputs, they may actually run into bugs, right? And similarly, debugging becomes challenging because in order to reproduce this buggy execution, we have to reproduce exact the same input, right? All the input coming from the environment, all the bits have to match, which can be hard, for technical reasons or privacy reasons. And by the way, we actually did observe this behavior. If we change input slightly, the bugs show up. If we change input more, the bug disappears, right, with existing DMT systems. So to address this instability problem, to reduce these unstable behaviors, we propose an idea called schedule memoization. The idea is to memoize the schedules that works in the past, right? And then in the future, when input comes, we can try to reuse these schedules, right? Therefore, we can avoid potential unknown schedules and also buggy schedules. And we call this stability, right? So we hang on to the good schedules, well-tested schedules. And in the future, if new input comes, we'll try to reuse these schedules that are shown to work. Therefore, we can avoid bugs in the unknown schedules. Do you guys questions? So actually, a typical question I got here is, if you do this, right, you sort of live with the program which contain bugs, right? Because you hang on to the schedules which do not contain bugs, and the program itself is not very, very correct, right? And my answer is, this can be turned on, right? This technique can be turned on for production systems, right? We will actually deploy the system, we will ship the code to users. You can hang on to the good schedules, right? And avoid the schedules we have not tested, right? But in testing, you can turn this technique off and use techniques such as chess to actually explore different schedules and get a set of correct schedules, right? Therefore, and then ship the schedules together with the program to end users. Question? Right.
Go ahead.
So are you going to explain what do you mean by the same schedule?
Yeah, I'm going to explain that. I'm going to define schedule, what schedule is, right? Like in the next few slides. So we actually call our the first system that implements this schedule memoization idea turn because this idea actually matches our natural tendencies, right, in animals and humans. We repeat familiar routes and avoid errors in unknown routes. And this slide shows the migration routes for birds, right? So basically, migrant birds, they follow these fixed routes. They don't run into random routes. And our system, the first system that implements schedule memoization is called tern, which is after this Arctic tern bird, and the bird species that migrates the longest among all known animals. Okay, that's a picture of Arctic tern. Okay, so now we can reuse schedules for different inputs, right? But a key challenge still remains, which is from determinism or efficiency, right? You can only pick one, you cannot pick both. I'm going to explain what I mean by determinism and efficiency in the next few slides, and also define what a schedule is. So at the language level, where does non-determinism come from? It comes from mainly two sources. First, we have non-deterministic synchronization. For example, locks, right? So locks can be acquired in different orders. This slide actually shows a bug in Apache that's caused by non-deterministic synchronization. So the first thread acquires a lock and uses an object, shared object. And the second thread frees this object. And they both compete for the same lock. If the code is run in this order, the code is correct. However, if it's run in the reverse order, right, because we have this non-deterministic order in terms of lock acquisition, and the code will run into a use after free crash. So here, this piece of code crashes or runs correctly depending on synchronization order. Another source is non-determined source is data race. This slide shows a data race example from one of the benchmarks we use, FFT implementation in Splash 2, a popular parallel benchmark. So here, this first thread 0, prints out some results, and thread 1 actually computes the results, right? There's a computation, there is a print, right? If the race is resolved this way, we get correct results. However, if the race is resolved the other way, we actually print out wrong results, right? So here, this piece of code prints out correct or wrong results, right? Depending on how the races are resolved, right? The order of memory accesses. To eliminate these two types of non-determinism, researchers have proposed two types of schedules, right? The first is called sync schedule. Basically, it's a total order, deterministic order of synchronization operations, such as lock and unlock operations. The second type is a deterministic order of shared memory access operations, right? So we enforce the order on load and store operations to the same memory location. So both types of schedules have pros and cons. So sync schedule basically, for this particular example, if we just enforce this order, right, or we enforce this order, either way, right, we can make this code deterministic, right? The bug always show up, or the bug always not show up, right? So the advantage here is it's actually very efficient, right? You enforce a total order synchronization operations, so most of the code does not control synchronization, therefore they can still run in parallel. Overhead reported is average 16%. But the downside is, if there are data races, right, this approach won't work, right? Let's look at this race again. We can enforce a deterministic order on the barrier synchronization, right? But at the same time, this race can still be resolved in different ways. Therefore, you can still have non-deterministic behaviors. The second way to to make program deterministic is to enforce this memory access schedule, right? And for this particular example, if you can always enforce this order, right, or this order, either way, right, we can always enforce the same consistent order. We're going to make the behavior consistent, right? Either the bug always show up or the bug always not show up. But the problem is, this is deterministic, right? That's the advantage. But the problem is, a normal program does lots of memory accesses when you run it, right? Shared memory accesses. If you enforce these orders, you can slow down the program by a lot, right? So the number reported in the previous system is from 1.2 to 10x slowdown. Question? Question? All right.
So in these, there are two kinds of overheads, right? So one is the instrumentation overhead, just by having to do some extra work on each memory operations.
Right.
You're going to pay some cost.
Slow down things, right?
And then there is this other cost of actually enforcing the determinism, where the hardware has more parallelism, but you're not able to use that because you want to enforce determinism.
Right.
So do you know how we can, how to split the overhead?
That's a good question. I actually do not have specific breakdowns for the instrumentation overhead for memory access, right? But for the synchronization order overhead, right, like this. So right here, if you enforce this synchronization slowdown, right, and this overhead actually comes mostly from waiting, right, because there are just too few synchronization operations in code, right. And here. So for memory access, I think the instrumentation alone gives you maybe like 5x, 10x slowdown, right? So it's reasonable. The waiting time may not be that critical here, right? Okay. So the challenge here is, either we pick sync schedule, right, enforce a synchronization order, or we enforce a memory access order. But if you use sync order, we do not get full determinism, right? Because if there are data races, it's not deterministic. At the same time, the code actually runs efficiently, right? If we pick memory access order, we get full determinism. If there are data races are resolved deterministically, right? At the same time, we get this efficiency problem because the slowdown can be quite a lot. So can we actually get both? So with Peregrine, you can actually get both, right? You can get both determinism and efficiency. And I explain how we actually computed that. As one key idea in Peregrine is, we can enforce hybrid schedules instead of mem schedule or sync schedules. And the insight here is that races actually rarely occur, right? So although most programs have races, right, either benign or harmful, but these races in practice actually do not occur that often. Intuitively, if your program has lots of races, right, you run it in testing lab, right, you probably have detected these races already. Empirically, we actually run 6 programs that contain races, and we run some standard workloads such as compress a file for a parallel compressing utility, right? And there are millions of memory accesses, thousands of synchronization operations, but we detect only up to 10 races, right? So the races actually do not occur that frequently. So if you look at, let's say this is an execution, most part of the execution is actually fine, do not contain races. Only the minor portions actually contain races, right?
So what does it mean for an execution to contain a race?
Contain race, which means there are concurrent memory accesses, right? You can flip their order, right?
Do they happen at the same time, or using happens before?
Using happens before. Using happens before, right? So the access is, you have one access here, another access, right? And if you look at the absolute time, right, they're not concurrent, right? But they could have been reordered if you run it again, right?
So this 10 or 10 happens before races.
Right, 10 happens before races, right? With respect to the synchronization order we track, right? And I'll show you more details when I talk about the example, right? So it's not, you run a regular dynamic race detector, can detect a lot more races, right? But here, we assume that we enforce a more stringent synchronization order, right? Which actually prevent a lot of races, right? Okay. So based on this idea, right, based on this insight, we propose to actually use hybrid schedule to combine the benefits of both sync schedules and mem schedules. The idea is, for these portions, right, which do not contain races, let's just use sync schedules, right, enforce the total synchronization order. We get determinism, we get efficiency. And for this portion, right, the minor portion that contains races, we can enforce a more expensive memory access schedule. And here we have more overhead, right? But if this portion is only a small portion of the entire execution, the overhead won't be that high, right? And we implement this idea in a system called Peregrine. And this picture actually shows the Peregrine falcon, which is the fastest flying bird. Specifically, how do we actually compute hybrid schedules? And the idea of schedule memoization actually makes it very easy to compute hybrid schedules. The first, when we run the program on the input, right, the new input we have not seen in the past, we'll record an execution trace which contains both synchronization operations and also memory access operations, right? Their order. And we do that because we do not know if this execution will run into races or not. And once we've done that, we have this execution trace. We're going to run some offline analysis on the trace to relax this trace into a hybrid schedule. And this hybrid schedule contains synchronization operations for the read part, right? And memory access schedules for the receive part. And with this schedule, in the future, if there's an input compatible with this schedule comes, we can reuse this schedule on this new input with both determinism and efficiency. So why can't we actually reuse schedules, right? Let me actually ask this question. Think of a simple parallel program such as parallel compression, right? PPT2 in our benchmark. It splits the file into multiple blocks and then compresses these blocks using multiple threads. As long as you make sure the number of file blocks and the number of threads remain the same, you can compress a file using the same compression schedule, regardless of the file contents, right? So often the case you can actually reuse these schedules. And in our evaluation, we actually found out that for programs such as Apache, you can reuse schedules 90% of the time for many programs, not just Apache. And also, this part, the reuse part, right, requires some analysis. And in the Peregrine system, we made this part automatic. It does not require user annotations. Question?
So for every new input, you need to know which is a data race free portion and which is.
So depending on what we mean by new input, right? So once you figure out one schedule, right, we're going to compute, okay, for this set of inputs, you can totally reuse this schedule without introducing new races at runtime, right? And therefore, these inputs will be covered by this schedule, right? If there is some new schedule that is not covered by your existing schedules comes, right? And that input requires this new analysis, right? Okay.
So you're going to have details on.
Right, I'm going to show you an example, like explaining how this works, right? Question?
You're probably going to talk about it later, but where did you get the inputs that you tried with Apache?
For Apache, the input comes from the network, right? So actually hooked the receive method, right? The receive system call to receive network data,
I'm just
right?
wondering, because it really depends on how different the inputs are.
Right.
I'm just wondering, what set of maybe probably HTTP requests, how you generated those requests.
So we generate the request by using two methods, right? One method is actually run this synthetic testing tool, right, which launches a bunch of ATV requests, right, fetch different URLs, right. And the second type of workload we got is from the trace from the Columbia website, right. So we collected like 1 month trace from the website, and look at all the ATV requests issued to the Columbia CS website, right. And then in our evaluation, we actually launched these ATV requests to our system, right, and figure out the reuse rate, right. Does this answer your question?
Yeah, were they mostly static or were they static combinations?
It's mostly static, those ATV requests. Okay. So our system also handles piecewise synchronizations. It runs in Linux, right, and also for deployability, we actually made our system run in user space instead of modifying the kernel. And also it works with server program like Apache, right. So I'm going to show you the summary of results, right, before I talk about the details of the system. We evaluated Peregrine on a diverse set of 18 programs, including programs such as Apache Web Server, parallel compression utility PBZ2 I just talked about, and also AGET, the parallel file downloader, and also PFScan, a parallel file scanner. We've also evaluated our system on 13 scientific programs, right? Programs implementing scientific algorithms, 10 from the popular Special 2 benchmark and 3 from popular Parsec benchmark. We also tried a program called RISI, which contains tons of RISIs. And this program is actually a stress testing tool for deterministic replay and deterministic execution, right? Because if any RIS is resolved differently, you'll get different results, right? This RISI benchmark, stress testing tool. And Peregrine can deterministically resolve all the RISIs in these programs. So we determine them. And the overhead is, it sometimes can actually speed up the program by up to 54%, and the overhead is up to 49%. And it can also frequently reuse schedules for 9 of the 18 programs.
How does this speed things up?
The speed up, basically, okay. So there are two key things where we can actually speed things up, right? The first is once we enforce a synchronization order, right, we can replace expensive synchronization operations with cheaper ones, right? That speeds things up. For example, there are operations such as barrier wait, right, which cause an unconditional context switch, right? That can cause a lot of overhead, right? But once you enforce the order, you can use cheaper ones. Just do not context switch, just spin wait, right? That can make it faster. And also, some of the benchmarks actually use mu sleeps for synchronization, right? So they do not use explicit synchronization. They actually use mu sleep to sleep for a while and then synchronize, right? But once you enforce the order, you can actually skip all the sleeps, right? So that's why we can speed things up. Okay, so let me show you an overview and then talk about how the system is implemented using a detailed example, right? And then show the evaluation and conclude. So Peregrine actually uses both runtime components and compile time components. So given a program, right, first we're going to instrument the program using our instrumenter, which runs in the LVM compiler infrastructure. And at runtime, we maintain this key data structure called schedule cache, which contains a set of tuples, C constraints, right, as schedule. So this is a hybrid schedule. S is hybrid schedule, and C are the preconditions required for us to reuse this schedule on new input. So just talk about this parallel compression example where if we maintain the same number of file blocks and the same number of threads, we can reuse the same schedule all the time, right? But however, if the input actually changes, right? For example, we want to compress a file using more threads, right, or less threads, fewer threads. We need to determine that this schedule is not compatible with the input. We need to use a new schedule. How do we do that? Well, we actually capture these constraints in these preconditions, right? So when I get a new input, we can check the precondition and determine whether or not we can reuse the schedule. So let's say the input comes, right? We first do this lookup in the schedule cache to figure out if the input matches the preconditions. And if they do not match, right, we forward this input into a component called recorder, which will record a detailed execution trace, including synchronization operations, memory access operations. And then we run this offline analyzer to extract a hybrid schedule and the precondition required to reuse this hybrid schedule on new inputs. Extract this new tuple and then put it into the schedule cache. And if the input actually matches this schedule cache, right, it's simple. We just forward the input and schedule to the replayer, and the replayer will run this program while enforcing this schedule S. And because the analyzer can compute correct preconditions, we can be sure that this input can always be precise by the program while enforcing this schedule S. So, okay, so I'm going to show you, this may sound like very abstract, just a bunch of conceptual ideas, right? So let me show you how this works using a real example. So this code is taken from the PB2 and also FFT program in our benchmark, right? So it's simplified to fit within this slide. And it first reads some input, right? And then it spawns a bunch of worker threads to process some data set. If you look at the worker thread, it does some memory allocation, and read data and do some computation, right? So this is simplified, right? So the real code is more complicated than that. And then it updates results by grabbing mutex, update this shared variable result, and then release the mutex, right? And the main thread also participates in this computation. It calls worker as well. And optionally, the main thread also updates this result based on the third argument, argv3. And then it prints out the result, right? So this code actually contains a bug. Can you guys see the bug here? Right, so there's a missing piecewise join. This code can actually run in parallel with this update code, right? So therefore we can have races, write races or read write races, right? That's one example. So given this piece of code, we'll first prepare it for use at runtime by running it with the instrumenter. The instrumenter will first annotate, intercept all these lines that actually read inputs, right? For example, the lines that access argv, right? The command line arguments, they are considered inputs to a program. And this myRead function calls the system call read to read file data. We also instrument this read system call to mark that data as input. And given this input data, at runtime, we can track how the input data is used. Therefore, we can compute the preconditions required for reusing some certain schedules. And this instrumenter also actually instruments all the synchronization operations, such as lock operations, this piecewise create, so that we can record schedules. Let's say after instrumentation, right, we got the instrument program. Let's say we run this program with this particular set of arguments, right? 2 to 0, which means we're going to spawn 2 threads. We're going to process a data set of 2 bytes, right? And 0 means we do not actually update this result optionally, right? And the recorder will record a detailed execution trace. We're going to record the statements that reads inputs. We're going to record the execution of this loop as well. Since the number of threads is 2, so the first time this I is compared to n thread, we get this true return, right? And the second time we compare 2 to n thread, we get this 0 return, right? So this code corresponds to the execution of this loop. And we run this worker thread, which also we also record all the statements activated, instruction activated, right? Also, this gray area corresponds to the loop here. And similarly, we do the same thing for the workers called by the main. And then this main function will update the result by grabbing this log. And the child thread, the worker thread will also do the same thing. And we record the output of this comparison, right? Flag to argv3. Then the last statement is to print out the result. So once we get this trace, I'm going to show you how we can actually extract hybrid schedules and also constraints. So first, we're going to copy all the synchronization operations to the hybrid schedule. And we also enforce their order, right? So if the order in the execution trace is at this, right? In the future, when we reuse the schedule, we're going to enforce the same order. And next, we're going to detect races with respect to these synchronization operations, right? And there are 3 accesses to shared variable result. And if you look at the first pair, they're not a race, right? Because there is a synchronization order constraint here, making them not concurrent, right? But here, these 2 threads can totally grab different locks, right? And we would not flag this as a race as well, right? Even though the locks are different, but we're going to enforce this total order of synchronization operations at runtime. Therefore, these 2 accesses will never happen concurrently, right? Therefore, they are not at race, right? Does this answer your question? Okay. And let's look at the other 2 accesses, right? These 2 accesses, there are no synchronization operations in between. They can happen actually concurrently, right? Therefore, there is a happens before race detected as well. And to resolve this race, we're going to add 2 memory accesses into the schedule. And we'll enforce an order between these two accesses, right? So that in the future, when we use this schedule, it's totally deterministic. So once we get the hybrid schedule, we need to compute the preconditions required for reusing this schedule. So how do we do that? One naive approach is we can, okay, so there are a bunch of challenges here. Right? First, the preconditions need to ensure that all these events are reached when we rerun this program on the future input, right? Enforce feasibility of all these events, right? That the events can be reached at runtime. And also, for determining them, when we use schedules, right? We want to make sure that we don't get new data races, right? Because if there are races, the execution results can be different. So this slide actually shows an example of a race that may show up if we just reuse this schedule, right? So let's say we enforce this schedule, but this argument, right, this argv3, right, becomes true, right? So that this becomes 1, right? And this flag is 1. This particular check, right, satisfies. Therefore, we're going to run the true branch of this statement. We're going to access result, right, which actually races with these result accesses, right? So there can be new races coming up if we reuse the schedule on new inputs, right? So these are the things we want to avoid as well. We want to avoid new races. So how do we do that, right? So one approach is we can look at the conditionals, right, executed in the trace, and if the conditionals depend on input, right, that means if the input changes, the value, the result of the conditional may change, right? We can grab all these conditionals, right, and use these conditionals as the preconditions, so that in the future, if input satisfies these conditionals occur, right, we're guaranteed that all threads will go down the same path, right, following the execution, right? Question?
Could you say a little more concretely what constitutes input?
So input, here we consider input as the arguments passed to the command line, right? And also inputs read from the network, and also input reads from file.
Okay, so does inputs also include things like if I look at the timestamp, or I look at
So,
the system load and decide how many threads to spawn, or I'm getting, like a signal goes off during execution and that causes
right.
me to take a different path. There's a lot of non-determinism.
Right. So the signal part, currently we actually do not handle. The get timestamp part we currently also do not handle, right? So if the code actually calls get time of day, right, get back the value, and that value affects synchronization operations, right? That's something we do not handle. And the things we handle are, for example, the random returns, right? So if the program calls random, right, gets back value, right, and we can just mark it as input and do the same thing, right? And for get time of day, you could have used the same approach, right? But the thing is, if the get time of day return value is not integer, right, it actually cannot be tracked by our constraint solver, right? So that's a limitation of our system, right? Okay.
So random is deterministic, right? If you just
set the same random value, right? So you can
random number generator is
sure.
deterministic.
You set the same random seed, right? Like you get the same value, but you could be reading things from dev/dev/random, right? At runtime, right? Those can be totally random depending on the system setting. Okay, so these are our constraints. And if input matches all these constraints, we go down the same path, right? Therefore, we address all these challenges, right? And these constraints actually can be further simplified to be this, right? So these are the simplified constraints. The problem with this naive approach is it's actually computes over-constraining preconditions. For example, let's look at this size is 2 constraint, right? It says, in order to reuse this schedule, right, the hybrid schedule we just computed, you have to make sure that the data size is 2, right? But actually, this schedule. So this synchronization schedule, right? If you look at the piecewise create, all the memory accesses, right? You can actually reuse it on a lot of different data sizes, right? Even if data size is now 2, it actually doesn't matter. So in some sense, this size is 2 constraints actually were over-constraining, right? It precludes a lot of the opportunities where we can actually reuse the same schedule. And one way to solve this problem would be to throw away the constraints that do not matter, right? But how do we actually figure out what constraint matters and what constraints do not matter, right? That's one of the challenges when you solve here. It turns out this problem is very hard to solve. Solve most of our efforts in this project. Since then, we come up with some program analysis techniques. And the first technique is to slice out instructions that do not matter, do not affect schedules. And second technique is to improve the precision of the first technique, right? We actually need to simplify the program toward a schedule, and therefore analyze the simplified program so that we get better precision. So the details actually are described in our paper, and also I'm happy to discuss the techniques with you guys offline, but it's just too complicated to include in the talk. And then intuitively, here's the intuition, right? Intuitively, when you look at this computation loop, right, it concerns only thread local variables, right? So local data. For example, this data is allocated locally, right? It's on, in some sense, it's private data for this thread, right? It's on a private heap. And this computation, right, reads files, do the computation, but actually doesn't touch the data accessed by other threads, right? So it's local computation as well. So these local computations, right, can actually be sliced out.
So I have a question.
Okay.
So what makes a relaxation appropriate for you? So if I relax the constraint to something,
right,
how do you know that that relaxation is still okay? Does it mean that for any state in there, this particular schedule that you computed is still feasible? Is that what you want?
It's still feasible and does not introduce new races, two conditions.
Does not introduce new races also.
Right, because remember there's this conditional update of the results, right? So depending on the third arguments, right? If you run it on a new input and there's a new race coming up, right? And the results may be non-deterministic depending on how the race is resolved, right? So those are the two conditions. All the events are feasible, right? At the same time, no new race is coming up. Okay, so there is some path slicing work, right? And the algorithm can be used to solve part of the problem within a sequential execution, right? But here you need to look at inter-thread dependencies, right? If I read a particular variable here that's defined by another thread, right? There can be diffuse chains across threads, right? That can make things complicated, right? So that's part of the problem we solve here, right? Make it concurrency aware, right? Okay. Right. Question?
Do you do all the analysis? Those analyses statically?
We do this analysis statically in the sense that you get the program, you get the execution trace, right, and then you do the analysis, right? And it's offline, right? But you use this dynamic information because we have this dynamic trace, right? Okay, so it's a combined dynamic and static analysis.
So
right?
You are doing all these calculations
up
front as part of the training phase. So when the program is actually deployed, all this stuff is not being done, right? All this calculation business.
So you can imagine that we could do this also at runtime as well, right? Updating the schedule cache, right? Sure. But right now the analyzer runs for a long time, right? So doing it online does not make a whole lot of sense because it's slow, right? Yeah. So the ideal mode would be that even if after you deploy the system, you can still collect schedules, right? But you still run the analyzer offline to update the schedule cache instead of updating it online, right? Okay.
Do you use symbolic execution at all? How would that help or not help?
What's help?
Symbolic execution.
Symbolic execution?
Yeah, figuring out what inputs affect what conditions.
So basically, once you slice the program out, right? Once this statement is sliced out, we get this smaller slice, right? We actually run symbolic execution to get the constraints, right? So we look at input dependent, we track how input propagates within the trace. We track, the condition nodes on the input, right, and then collect constraints, right? That part is done by symbolic execution. We leverage symbolic execution, right? Okay. Okay, so once we slice things out, right, like all these, statements, they're irrelevant, right, to the schedule. We slice them out. We get the preconditions. We simplify them. These are the final preconditions, right? So this is a hybrid schedule we learn from the trace. And these are the preconditions we compute for reusing this schedule. And if we run this program on a new input, let's say 202, right? It says we want to spawn 2 threads, process a data set of 100 elements, and then the third argument is 3, right? And this input data, right? The arguments will match the preconditions. Therefore, we can reuse these schedules and enforce the schedule, right? To determine them. So there are a few benefits of this approach. The first, we can actually deterministically resolve races, right? Like this race is deterministically resolved. And also the preconditions computed, we ensure that there won't be new races coming up when we reuse the schedule, right? So determine them. And also it's very efficient. As you can see, we enforce an order on these synchronization operations plus only 2 memory accesses, right? And the major computation part, right, can still run in parallel. And also, this schedule can be reused across a bunch of different inputs, right? We don't care about the data contents at all, right? And we do not care about the data size, right? So you can give me different data set. We can still reuse the same schedule. So questions so far? Okay.
Rather implementation question.
access. So we actually instrument the program, right? So when there is an access here, right, we put a semaphore operation up here, right? Before this access, we put a semaphore operation down there, right? So they form a constraint, right? So like you can.
You would dynamically actually instrument after you
Right.
figure out what schedule to use. You would dynamically
instrument the program, right?
So Madan made this point that if you instrument a program's memory accesses,
right,
but to do nothing, just a no op, right?
Right.
You automatically start paying 5 to 10 times overhead.
Right.
So how are you avoiding that?
So if you do that for all the load and stores, right, you get 5 to 10 slowdown, right? Maybe even more, right? But here we just instrument these two specific accesses we know, right? Because these two accesses are involved in races. And all the memory accesses here, they can totally run in parallel without any instrumentation, right? Because they do not involve in any races, right? So these two accesses, right, you get some small bit of slowdown there, right? But because we just instrument two, right? Just a few memory accesses, right? So you get away with smaller overhead, right? Okay, right?
So there's one other way of looking at this.
Okay.
What you could do is you essentially run one of the existing conservative data race detectors.
Right, exactly. Right. That's like
instrument only those accesses that participate in data races.
Right.
Because you're getting some of the effect too, right? So even though the result, that particular program point, let's say if it's in a loop.
Right.
So it's because you're instrumenting it, you're going to pay the cost of
Right.
instrumentation and
Exactly.
the loop.
Right.
Even though
that's a great
different
observation.
pointer might have been accessed in each iteration, right?
Right. Actually, do guys have good static race detectors? So this is some idea we actually are interested in pursuing in the future, right? You can do static race detection and figure out the race points, right? And then schedule them together with the synchronization operations, right? Therefore, get deterministic multithreading and efficient as well, right? But we checked one of the state-of-the-art race detectors for C programs, right? And it has a really high false positive rate. It's like for each function you get maybe 100 reports, right? So do you guys have like good static race detectors we can leverage, we can use?
Nothing fully automatic inside the company, I think. But there's an annotation-based race detection.
I see. So add some annotation, speed up.
It's modular and it's based on contracts and things like that.
Right. Maybe you can collaborate.
Okay.
Right. We would be interested in using such a race detector, right? So right now, another direction we're looking at is not just for C programs, for Java programs, right? There is a race detector developed by Alex Aiken and his students, right? And they have good precision, and also I think the second version of the system is sound, right? We're looking at whether or not we can actually do this for Java, right? With that powerful race detector, right? If we can get the C work, right, or C++ work, that'd be a great thing to do, right?
Why do you need to also order the logs and unlocks, the synchronization options? If you just do memory, you'll be doing pretty much the same thing, right?
So if you just do memory, right, you can get determined, right? We know that, right? So you can enforce the deterministic access for shared memory operations, right? But at the same time, you pay a high overhead, right? Because you have the instrumentation overhead, instrument each load and store. You have the wait overhead, right? Because you cannot do a memory access if all the ones prior to the access are not done, right? So there is a wait overhead there as well, right? And the overhead can be up to 10 times, 11 times, right? Based on previous papers.
But this lock and unlock,
This one?
it has the same overhead because you have to, if that lock comes first, you have to wait until that unlock is not first. So if you order that result between the lock and unlock on the left with the results on the right, then you won't need the unlock and lock.
So, okay. First of all, there are two questions here, right? The first question is the overhead of instrumenting and controlling the order of synchronization operations, right? The second is, if we do this, enforce this memory access order, right, do we get roughly the same overhead, right? And for the first question, instrumenting these intercepting synchronization operations tends to be cheaper, right? Because these are already library calls, right? You can easily hook them, right? And instead of you hook load and store operations, for each load optimized code that contain load and store operations, you do a function call.
But you're already doing that, right? You're already doing that for the first run, and then you.
Right. For the first run, we do that, right? But for the future run, we don't do that, right? So we can avoid overhead for the future runs, right? The first run, the overhead is as much as the existing tools that enforce memory access order, right? So instrumenting those, right, does not give you a lot of overhead, right? The first, right? The second, if for these two particular access, right, if you enforce this constraint, right, and you probably will get roughly the same overhead as enforcing this constraint, right? But at the same time, there are lots of memory accesses here as well, right? And how do you know whether or not you want to enforce order for those accesses, right? Memory accesses. If you do enforce orders, you get slowed down, right? If you do not,
that you figure out that you need between that result and the result down there, can't you figure the rest of them out the same way?
So we actually here we know that there are no races between these two pieces of code, therefore we can slice them out, right? So are you suggesting that for this particular access, right? This result access, we just add this edge instead of adding this edge, right? But these two access actually they do not race, right? If you're using your algorithm, they do not race, right? Therefore you will not add an edge here, right? Therefore you can get non-deterministic synchronization, right?
Yeah, but you're already adding the unlocking log edge,
right?
Which means that there is a race if that didn't exist, right?
So we do this, right? Actually to resolve the race on the lock, right? So this guy grabs one lock, this guy grabs the same lock, right? They can grab the lock in different order, right? Sure. Therefore, you can get different results.
Sure.
To add this edge to say, okay, this guy always get the lock first, right?
Yeah.
Therefore, you do not have this non-deterministic lock contention, right? But it doesn't matter, it doesn't involve these two accesses.
I agree, but what I'm trying to say is that what you're doing there is fundamentally basically trying to have an edge between the memory location of the lock itself, right? Kind of like that. So if you didn't have lock and unlock and you had custom synchronization, that what you had to do that. You had to basically have the lock memory and then have one of these arrows between them, right?
Maybe a better way to look at this would be that it's sort of similar thing, right? So the lock non-deterministic lock operations, right, translate to non-deterministic access orders to memory accesses. Maybe a better way to look at this would be that here I show you an example with just one access, right? But you can have a large critical region with lots of accesses, right? And if you ignore synchronization operations, right, just enforce order for memory accesses, you're going to enforce a lot of edges, right? Therefore, you may get better performance, right? But right now, we just look at the synchronization. I know this synchronization. I enforce this synchronization order, right, which automatically covers all the memory accesses within the critical region, right? Therefore, it's going to be more efficient, right? Okay. Okay. So our system actually has limitations as well, right? Some folks just pointed out. So first of all, my big assumption here is we can actually reuse schedules, right? Which may not always be possible. For example, you actually want non-determinism in your simulation to get some statistically sound results, right? So those workloads or programs, right, will not fit within our approach. And also, by enforcing some deterministic order of operations, right, memory access or synchronization operations, we sometimes introduce delays, right? If your program actually is latency intensive, that's not a good workload for us, right? And also, we need to keep track of constraints in order to figure out the preconditions. And our current engine only tracks constraints on integers. If you have floating point operations, the schedule actually depends on floating point, which we cannot handle. And we also require source code or the RLVM, the compiler intermediate representation, the bit code. That's another limitation. And currently, we do not handle non-determinism coming from get time of day or malloc, right? So if you malloc something, you get a memory address, and you do some non-deterministic synchronization based on the return address of malloc, right? We cannot handle. Though actually, this probably can be handled using some existing techniques, right? For example, there are implementations of heap implementations that actually are deterministic, right? And also, we work only with a single process, right? So this doesn't work if you have multiple threads sending messages to each other, right? Although we're planning on, making this approach work for MPI programs as well, right? Or programs that communicate by sending and receiving messages. So,
do you also determinize the order of system calls?
Right now, no. So we don't determinize the order of system calls, right? You can have race inside the kernel, right? Possible. Okay, so there are lots of applications we can do on top of this idea, right? At a basic level, you can simplify program understanding, testing, debugging, right? Enforce the same schedule, test the schedule at the production, right? And also you can use it for doing deterministic replication of multi-threaded programs, right? So when program runs, has some non-determinism, instead of logging and sending the non-determinism, if the input hits the schedule cache, you just reuse the same schedule automatically, right? Therefore, it's deterministic. And you can report bugs without reviewing the full input, right, which may contain your credit card numbers. And also, once you have the schedule, right, you know what the program is going to do in the future, therefore you can do some scheduling trick there as well, right? And actually, another very interesting application we're currently exploring is we can use this idea to build some precise static analyzer for multi-threaded programs, right? So I briefly talk about this idea. So when we analyze multi-threaded programs, we can use dynamic analysis, right, which analyze the schedules that are occurred, right? And it's basically unsound because the next run of the program we actually use a schedule that's not analyzed, right? And we can do static analysis of all schedules, right? But that requires a lot of approximations, right? And sometimes we get imprecise results, right? Like risk detection, you can get tons of false positives. With Peregrine, you can actually solve these, address these issues to some degree, right? And we can analyze the program only with respect to a small set of schedules, right, that are being enforced as runtime. Therefore, we can get precision, right? We don't need to assume all possible schedules, just a small set of schedules. And also, we can enforce these analyzed schedules, right, at runtime using Peregrine, right? Therefore, we can guarantee soundness at least for these schedules, right, the schedules that we analyzed. And if there are new schedules, that are required at runtime, right, we got a new input that cannot be covered by these schedules, right? We need to, learn this new schedule. And for these rare cases, we can actually use some, expensive techniques such as we do, simulation of the program, right, to guarantee, to check for errors, for example. And under the assumption that, this most, under the assumption that we can frequently reuse schedules, right, so most of the inputs, right, 90% of the inputs can hit the schedule cache, right, we can actually guarantee precision and soundness for 90% of the input, right, which I think is it's a good contribution. And by the way, this is some ongoing work, right? So we have this idea, we did some preliminary study and get some results, right? And this is not published yet. Okay, so one challenge here is how do you actually analyze a program towards just a small set of schedules, right? When you do static analysis, we don't have this notion of schedules, right? And one approach is, modify every static analysis to say, okay, this is schedule, right? Take that schedule into account when you analyze the program, right? But that's kind of strenuous, right? Because you have to modify a lot of analysis. And also, sometimes when we build a tool, we compose a bunch of analysis together. If there's any imprecision in one of the analysis which does not consider schedule, right? And the imprecision may actually propagate to other analysis, right? There are issues here. This is the naive solution I just talked about, right? Modify every analysis, which is not very practical, right? So our solution is actually, taking this program, right? Let's take this program, let's take the schedule, right? We can specialize the program toward the schedule, right? So that at runtime, when I run this specialized program, it's going to generate executions matching the schedule, right? So you transform the program to get a simpler program. And this transformation specialization process involves specializing the control flow plus the data flow of the program, right? For example, when we look at data flow, we only look at def use chains allowed by the synchronization schedule, right? The schedule we enforce. And you can have def defined here, use here, right? And you can have other load and stores on the same memory address, but if they're preclude, right, the data cannot flow because we enforce some certain schedules, we're going to ignore those def use flows. And once we get this specialized program, which is a lot simpler than the original program, right? Consider the schedule as well. We can apply stock analysis to the specialized program.
Do you think of the specialized program as an annotated program? A program, simply a program with annotations, or do you think that some statements get dropped or sliced away?
Some statements get dropped, some loop gets unrolled, and some data, some values, right, some variables become constant, right? For example, if the program, if the schedule dictates 2 threads, right, and the program uses a loop to create threads, right, and can say, okay, this loop bound must be 2, right, because the schedule only contains 2 threads, right? And you can propagate this value to all the other places where this value is referred, right? So you can view it as, it's a simplified program, not just slicing out statements, right?
So what you're doing is really optimization. You're optimizing the program by rewriting the code.
Okay, right.
To make it run faster.
So we're not sure about the run faster part. We're sure about the simplified
part. You are making it run faster. You said that. Examples. Right?
No, this is something else, I think.
What?
This part is
an application of the technique, right? So you can take the program, right? You do simplification, you remove stuff, right?
Yes.
And it may run faster, but we do not have experimental data to back it up, right? And we believe we can do some optimization.
That sounds like an interesting.
We're going to we definitely will pursue that direction, right? But right now our results is mostly on the precision part, right? So once you actually throw away a lot of crap and you specialize the program based on the schedule, right? You can do really precise analysis, right? For example, you get automatic thread sensitivity, right? Because the schedule says 2 threads, we're going to clone the thread function 2 times, right? Don't forget automatic thread sensitivity, right?
How do you, what I don't understand, how do you bake the schedule into the program?
Okay, let's look at the control flow part, right?
Okay.
So I have synchronization operations, right?
Yeah.
And I look at the control flow, I go from one synchronization operation to another, right? I straighten the program such that these two new statements, right, corresponding to the two synchronization events, right, become control equivalent, right? And the other path that bypass this synchronization operation gets chopped off, right? Because if you ever go there, you won't reach the second synchronization operation, right? And if there's a loop with 3 synchronization operations, right? And loop with 1 synchronization operation, right? And in my schedule, I see this operation appears 2 times, right? Then I know the loop must be run twice, right? And I can actually unroll the loop, right? So that's how we can specialize the control flow, right? Okay.
So it's funny to me because what you're doing is really the techniques that we do for optimization, like unroll the loop and so on and so forth.
Right.
But your goal is simplifying the analysis.
Right. So to get more precision, right?
Yeah.
So, question?
Sorry, can I ask? The specialized programs still will have threads, right?
Yes.
Okay.
We still have threads, right?
But is the semantics of the thread, usually when you have a multi-thread program, the semantics of the multi-thread program is that threads can context switch, statically at least, at arbitrary places.
Right.
The specialized program, does it continue to have the same semantics?
Yes.
Okay.
Right. So, we also need a dynamic part, right? So maybe this is what you're getting at, right? So I have synchronization operations in my specialized program, right? So these synchronization operations map one-to-one to my schedule, right? At runtime, I need some technique to enforce the order, right? That's why I say that, we actually need to enforce schedules at runtime using Peregrine, right? So is that what you're getting at? Or?
Yeah, that is what I'm getting at, because then the static analysis somehow needs to be cognizant. If you really want the static analysis to focus on those schedules, and the static analysis needs to be aware of these other edges, right?
Sure. So this is how we actually sort of get around the problem, right? So this data flow part, right? We're going to build this. We actually build this alias analysis, right? Which considers value flows, right? Based on the schedule, right? And then if you have another analysis which wants to query alias analysis, for example, right? You just query our alias analysis, right? And therefore, this alias analysis is made schedule aware, right? And if your analysis depends on the alias analysis, right? Your code, your analysis does not have to be made schedule aware.
I see.
Okay. Right.
So you're saying that there's some basic value flow or data flow analysis that you will provide. That'll put in some information there.
Right.
And you just query that as a black box. Other analysis just query that as a black box.
Right. Okay. So, we have some initial results. For example, we looked at alias reduction, right? So if you do not do this, do not fix the schedule, right? You get this many aliases, right? With the schedule, 99% actually gets thrown out, right? The precision is pretty, the increase in precision is pretty big, right? And we haven't, built a risk detector based on this technique yet, right? But actually, by running this analysis, right, and looking at the alias result, we actually detected, I think like at least 5 or 7, real races in the programs analyzed by a lot of previous systems, right? You see a lot of papers, they use the programs, right? But they did not report the races we detected, those are previously unknown, right? So I think that I'm very excited about this direction, right? So we're actually pursuing this direction yet, right? So, okay. So how much time do I have? Or do I guess I can wrap up, right? So you guys have seen the summary of results, right? So I just skip the evaluation. You want the evaluation? Okay. So which one do you, what?
So
overhead?
So one of the things that I'm worried about, not just QDoc, but in general, the whole deterministic multi-threading thing.
Right.
When you're enforcing the sync schedule,
right?
Let's say you run your program on a 4-core machine,
right?
And then you find a schedule,
right?
Then you try to run the same program on the same input on an 8-core machine,
right?
And you try to enforce the same synchronization schedule,
right?
I would like to know what the overheads are.
So the overhead? Okay.
So let me ask you. The more fundamental question is programs are non-deterministic for a reason.
Right.
Because then they can respond to environment changes, presence of more cores, like let's say you're running, suddenly 4 more cores become available because another process finished. Right?
Okay.
So they are non-deterministic for a reason to
Sure.
use all those computing capability.
Okay.
And so if you're restricting it by adding some determinism,
Right.
I would expect to lose some performance.
Right, so there is indeed some performance overhead, right? And for the particular test case, the workload you mentioned, right? So you get the schedule on a 4-core machine, right? You get this schedule on a 4-core machine, and then you run it on an 8-core machine, right? I would expect the schedule, the overhead, right, will be quite large, right? Because on a 4-core machine, you have lots of kind of switches, right? The synchronization order probably does not map really well to a 4-core machine, right? But for the scientific computation algorithms, right? So normally what they do is, if I have 4 cores, I'm going to just use 4 schedules, right? If I have 8 cores, I'm going to use 8 threads, right? 4 cores, 4 threads, 8 cores, 8 threads, right? So this number is actually part of your preconditions, right? It's part of your schedule, right? So on the 8 core, for some scientific benchmarks, right, we're going to automatically use the efficient schedule, right? In that sense, right?
So for those programs, I understand because at end, the number of processors, the number of cores is actually part of your input.
Right, part of the input. Right.
But if you look at more dynamic scheduling algorithms like class parallel library, what they're doing is I'm running Apache. At the same time, I also happen to be running Internet Explorer, right? And then Internet Explorer is using 2 cores, while Apache is using 6 cores, and then when Internet Explorer finishes, Apache sort of grows to use the remaining 2 cores. So there is a lot of dynamic scheduling algorithms, which are designed precisely to make use of these additional computational capability. So I would like to know what the overhead.
So my impression is that has always been the weak point of that entire deterministic multi-threading story, and they have swept that thing under the rug from day one.
I wanted to get your. So what is your experiments what did you find?
So in our experiments, right, these are actually those are mostly scientific programs, right? And these programs, they're desktop programs, we run them on 4 cores, right? And this Apache is basically, actually also run Apache to use all the cores, right? So we did not actually try the experiment use that, right? So my impression is that if we do the experiment you said, right, like you run a bunch of competing processes together, right? And you measure performance for some of the processes within this system, right? You may get a higher overhead, right? But I think there are, I can see 2 ways to address this problem, right? So I do not know whether these ideas will work, right? So one idea is, if the workload is actually predetermined, like these kind of computations, right? You have multiple processes, right? The processes want different number of threads, right? You can actually model them together, right? Look at them as a bigger deterministic execution, right? Deterministic execution framework, right? And there, you can capture constraints, use this approach, right? That's one way, right? Another way to potentially address this would be that, we can have not just one schedule for many inputs, right? We can have a few schedules for these many inputs, right? And then runtime, right? And this workload actually becomes a factor for us to choose what schedule to go, right? To use, right? And therefore, you can get efficiency, right? So in some sense, do we want one-to-one determine them, right? Probably not, right? Because if you change the input, you get really different schedules, right? Do we want many-to-one? Maybe, right? But you can also have many to n schedules, right? A small number of schedules choose at runtime to get performance, right? So those may be the way to go, right? So, right? I haven't tried these ideas yet, right? So, right? So do you guys want to see more results, or? So these are the overhead, right? So some of them, like we get speed up, right? Because they use barrier synchronization, which can be avoided by us, right? They use slips, right? And some of them we get bigger overhead, right? So.
What's the overhead if you don't get a hit in the cache?
So that's the recording overhead, right? Our current recorder is like 1000x, right? That's pretty slow because our recorder is not very optimized, right? So there are lots of papers talking about how to do efficient recording. We just haven't got the time to implement that yet, right? So that can be really large. If you look at the previous papers like IDA, right, developed by MSR guys, right? It's like 10%, right, to record the full execution stream, load store instructions, right? Okay.
So by Apache means, is it the whole Apache server? Or
right, the core Apache server, static HTTP request, core Apache server. If you do PHP, right, we haven't tried, right, but I think the PHP won't matter because it's single-threaded, right? You do a library call, interpret some PHP scripts, right, and go back, right? It's single-threaded, right? So you don't need to enforce schedule within the PHP module, right? Okay.
So I'm a little bit puzzled because you could just forget the whole story about determinism. And say, here's an automatic method to speed up programs. And it works fully automatically, and on these number of programs, they actually get better performance. End of story. No determinism needed.
Right. So maybe that's a better way to spin the work, right? So right now, we started this work by focusing on reliability, right? We want to avoid bugs, right? Avoid races. We remember schedules and avoid bugs, right? But right now, I think the static analysis framework we're really excited about, and also Jun, right? One of my fantastic PhD students is working on that, right? I think down the line we do want to do the optimization story, right? I think that can work well as well.
It looks pretty good if I look at that.
Right. So I think 50% improvement in bonds.
Right, but maybe the program were not written in a smart way, right? Because they use heavy synchronization, right? So it's arguable.
That's a selling point, right? You don't have to be that smart. That's good.
Right.
Say these are programs that aren't particularly skillfully written, now we
right.
can sort of improve them by figuring out what is a better schedule than.
Right, yeah.
And the wonderful thing about working on optimization is that you don't have to guarantee anything, right?
But you have to guarantee semantics is correct, man.
Yeah.
You just have to make sure you don't change the semantics or something like that, right? That's all.
Right, if there's a race, right? As you were saying, right? If there's a race.
I mean, there was some race there, right? I mean, let there be, it was in the program, right?
I see. That's actually maybe a better direction, a good direction for us to go. Right?
So, but the original sync schedule,
these are
the optimizations you're getting is sync schedule plus your optimizations, right? The sync schedule bars here.
So sync schedule gives us most optimizations, right?
So this is, but Kendo as implemented does not give you the speed up, right? You guys played some tricks with the sleeves.
Right, with the simulation operations, right? The optimization mostly come from the simulation operation, right? Okay, so right now, we do the simplification, we get the program, right? We analyze the program and get results, right? Actually, when we run program, I still run the original program, right? But the thing we haven't tried, right? I think that's a great suggestion is to actually run the simplified program, right? And also we can probably ignore races, right? The analysis part that deals with races because as Shard suggested, right? If the program has races, then it's the programmer's fault, right? You don't need to worry about the races. Right? Maybe you can get better performance, much better performance. Yeah, it's a great direction.
So do you know what percentage of memory accesses were synchronization and what percentage were racing? Like when you instrumented?
Okay, actually I have this number. Let me bring it up. Okay, so these are the races, basically. So these are the programs that contain races, right? Those are two real ones that have races, right? These are the synthetic benchmarks. They also contain races as well, right? Barney's. These are from the Parsec benchmark, right? So we run them, right? So the number of memory accesses can be millions, right? So several millions or even more. I don't recall the exact number. It's in the paper. The simulation operations on the order of several thousands, right? But if you look at the races with respect to the simulation schedule, right? They're pretty small number of races, right? These have 10. Partially, actually, once you enforce a single order, right? No races are detected, right? And for stream cluster, similar things happen, right? You enforce a single order, no races are detected, right? Okay. But intuitively, like most programs that you run, they do not have lots of races, right? I think that matches the general intuition. Any other questions? Okay, I guess I'll just conclude. So we talk about the schedule memoization, right? So memorize schedules and reuse them on future inputs, right? So we can reuse well-tested schedules and avoid potential buggy schedules, right? Also talk about this idea of hybrid schedules, right? It basically combines the benefit of sync schedules and mem schedules, right? As Madan suggested, right? You can actually you can implement this idea using a static race detector, right? Which actually we're currently looking at, right? And I also talk about this Peregrine system with it computes hybrid schedules by taking a trace and relax into hybrid schedules, right? And it's deterministic, make all these programs deterministic, efficient, overhead is low, and plus it can frequently reuse schedules. Okay, that's all.